Hi everyone, it's James again. This is Lab 8, which is Geometric Optics. And I'm going to show something first that may no longer be in the instructions. It's measuring the focal length of a lens using a very distant light source. If you look at the equation, 1 over f is 1 over d object plus 1 over d image. If the object distance is essentially infinite, if it's very large, 1 over d object is very small, essentially 0, so that 1 over f is equal to 1 over d image. So the image distance is the focal length, approximately. So if I take this 10 centimeter focal length converging lens and I hold it over the table, it's going to form an image of the overhead lights, which you can see if I tilt the camera a little bit. You can just barely see it. Yeah, you pretty much have to take my word for it. Well, no. There we go. Okay. So you see that bright light there on the table? That's the image of the overhead lights. And it may be too difficult for you to see, but if I move the lens to the correct height, I can see two separate lines of light, which tells me that I've focused two light sources that are close together overhead. And if I measure the height of the lens off the table, that's the image distance, because it's the distance from the lens to the image on the table. And if you see where my finger is, it is at 22 centimeters out of a little over 30, looks like 30 and a half, so it's measuring roughly 8.5 centimeters, so close to the 10 centimeter reported focal length of the lens. Okay, so that's measuring the focal length of a lens using a distant light source, approximately in this case. So, the actual experiment, we use this light bench, this optical bench rather. On it we have a light source, which I'm going to put at 100 centimeters, and the instructions say to put the 10 centimeter lens 20 centimeters away from the light source, and I'm measuring the position of the lens, which is at the center of the holder, by looking at the indicator line here, which is very hard to see, but it points to the position of the lens along the optical bench by pointing to the reading on the meter scale here. So I put this at 80 centimeters, and then I take the screen, and what I'm going to do is I have the object distance, the distance from the light source. This is a light source. Distance from the light source to the lens is the 20 centimeters I set up. That's the object distance, distance light source to lens. Then I'm going to measure the image distance, which is the distance from the lens to the screen on which the image is formed, by finding the place where the screen where an image is formed on the screen of the light source. So the light source is an L. You can see there's an image formed on the screen. That's an L. If I come too close to the lens, if the image distance gets too small, the image gets all blurry. You can barely see it. If I go back, then the image gets clear again. If I keep going back, if I go back too far, the image gets blurry and you can't see it. And so I want to find the position where the image is sharpest. And there's some uncertainty in that because there's some range over which the image looks as sharp as it does anywhere else in that range. And this is about the sharpest image, I think, here. And I measured this. This is so object distance is 20 centimeters. Image distance turns out to be 19. I'm going from 61 centimeters to 80 centimeters. That's 19 centimeters. For the image distance, object distance is still 80 centimeters to 100 centimeters, which is 80 centimeters to 100, which is 20. Okay. So object distance, 20 centimeters, image distance, 19 centimeters. And then I repeat that, and that will give me a measurement of the focal length of the lens and an uncertainty which I can compare to the nominal focal length of 10 centimeters and use that comparison as a test of the equation 1 over f equals 1 over d object plus 1 over d image, the lens equation. Okay, I also want to check the magnification equation, and I can do that by comparing the height of my object, right, this L, that's the light source. I can take either the bottom part or the vertical part and measure that length, and that's the object height, and I measure the image height, which is the length of the vertical part here, and I do that for these 5 measurements that are requested. As I move the screen, let's see here. I move the lens 2 centimeters closer to the source for the next one, so now object distance is 18 centimeters, and that's going to cause me to move the screen until the image is once again sharp, and it looks like it's about here. So again, I would measure this distance is the image distance, and I would measure the height here, and the height of the image divided by the height of the object would give me the magnification. So I can test the magnification equation and the lens equation. In other words, equations 2 and 1, respectively. Right. So I can compare the ratio of the image height to the object height, which is the magnification. I can compare that to the ratio minus d image over d object to test the magnification equation. Okay, I can also look at a stigmatism, which happens if the lens has a different focal length in the horizontal and vertical directions. Now let's see if I can actually show this in a way that you can see. I'm not seeing it. All right. Try tilting it this way. There we go. Okay. So as you bring the lens in, you can see that on the vertical portion of the L, see what's happening here? You can barely see it at least on my screen that I'm looking at. You can see that the vertical portion of the L is focused, but you don't see the horizontal portion of the L. And if you keep going in, the horizontal portion will appear, and there it is. Can you see it? Yeah, you can sort of see it. There you go. So closer to the lens, you get the horizontal portion. Further away, you get the vertical portion. And people whose eyes work this way have the misfortune to have parts of what they're seeing focused and other parts not. Okay, and that's astigmatism. Next thing is two lenses, and so we put I'm now looking at instruction 2.1. So I still have the light source at 100 centimeters, and I put the 10 centimeter focal length lens, the original lens, 20 centimeters from the lamp, as it was before at the start. And then I put the lens with a 5 centimeter focal length 50 centimeters from the lamp and record its position. So the 5 centimeter focal length lens is this, and I put it 50 centimeters away, so 100 minus 50 is 50, so I put it at 50 centimeters. And I put the 10 centimeter focal length lens back where it was, and then I'm going to move the screen until the image is clear. So I'm going to put so I have the light source at 100 centimeters, the 10 centimeter lens at 80 centimeters, the 5 centimeter focal length lens at 50 centimeters, and I'm going to put the screen over here, and I'm going to move the screen until I get an image of the L, which, if I followed the directions correctly, I ought to get, and I do. Cool. All right. And it's nice to calculate things out first, to verify the instructions. You can do the calculation with the two lenses to show that this is what you would expect. And I'm sure that you're asked to do that. All right. And the last thing is, but follow the instructions, whatever they say. Last thing is calculate the virtual image. So I'm going to move the first lens, which is the 10 centimeter focal length lens. I'm going to move it to a distance of 6 centimeters from the light source. Yep. So move it over to 94 centimeters, since the light source is at 100 centimeters. And there you go. And in this case, no real image is formed because the converging lens is only 6 centimeters away from the object, the light source, but it has a focal length of 10 centimeters, so the object distance is less than the focal length, so you form a virtual image, which means you can't project the image on a screen, but you can see the image because your eye has a lens of its own, and so your eye can take the virtual image from the first lens and turn it into a real image that can be projected onto your retina, so you can see the, quote, the virtual image from the first lens. And so the way you do that is you walk over here and you look through the lens, and I'm not sure if this is showing up well, but move around a little bit here. Maybe difficult to see. Anyway, when I look through the lens, I see a very big L that's upright. So in other words, I see an L that's upright, meaning it has positive magnification, and I see an L that's bigger than the object, L, from the light source, and so the magnification is greater than 1 in magnitude. So it's the magnification I measure qualitatively by looking through the lens is a number greater than 1. And if you calculate the magnification, which you will be asked to do, I believe, you will see that you get a positive number, and the number is greater than 1.